All right, guys, Gen Chem, we're going to do a little bit more practice with Le Chatelier. So here we've got dinitrogen tetraoxide gas going back and forth with two nitrogen dioxides. We see this a lot along the Wasatch Front, especially in the wintertime when we have that inversion layer going. That brown, smoggy, icky air is the dinitrogen tetraoxide, that brown layer. And the nitrogen dioxide is released from our automobiles as we drive around and burn gas. Okay. Notice we have this delta H being off to the side. It's positive. That means we have to put energy into this reaction. So that means that this is actually an endothermic reaction. So our energy is actually a reactant that takes energy. That's why that smoggy brown layer is at the very top of that inversion layer where that warm air is. That's where we can see that brown. Lower in the valley where it's colder when we have that inversion, that nitrogen dioxide is colorless and clear. Okay, so here we go. We're going to look at the stresses and see what goes on. Now, the thing is, we're going to look at also, and I don't expect you to do this, we're going to look at what it does to the equilibrium constant. Now, the only thing that actually changes the constant is the temperature. Remember, the constant is the products over the reactants. Okay? Only the temperature can change that equilibrium constant. No other changes will do that. Okay, so if we're talking about a certain thing, notice we're talking about N2O4, we're going to just blank that out. Okay, so we're going to increase our concentration of dinitrogen tetraoxide, which means our reactant side is going to get heavy. So we're going to shift right to our products. So our concentration of nitrogen dioxide is going to go up. So we're going to shift right, but this makes no change because we didn't change the temperature, okay, on our equilibrium constant. Nitrogen dioxide is increased, so we're going to exit that out. Okay, so if nitrogen dioxide is increased, that makes our product side really heavy. So we're going to shift to our reactant side. So we're going to shift left. Whoa, let's bring that back up. We're going to shift left. We didn't change the temperature, so our equilibrium constant is not changing. That means our concentration of dinitrogen tetraoxide is going to go up because we're going to make more of those reactants. Our temperature is increased. That's going to make that left side really heavy. So that means we're going to shift right to make more products. Okay? So if we make more products, that means our ratio of products over reactants is going to get bigger. So our equilibrium constant, because we have more products and fewer reactants, is going to actually get larger. So our concentration of dinitrogen tetraoxide is going to go down because we're shifting right, and our concentration of nitrogen dioxide is going to go up. Okay? I want you guys to do the next couple on your own, and let's see if you can do this. Okay, you guys ready to check? Okay, dinitrogen tetraoxide is decreased. That means our reactant side is going to get really light. So we have to shift left to make more nitrogen dioxide. We're going to shift left. That means our nitrogen dioxide is going to go down. And we haven't changed the temperature, so that's not going to. Our nitrogen dioxide is decreased, or our nitrogen dioxide is decreased, so our product side is going to be really light. So that means our dinitrogen tetraoxide is going to go down because we're going to shift right to make more nitrogen dioxide. And we haven't changed the temperature, so our equilibrium constant is not going to change. Our temperature is decreased. That's going to make our reactant side less. It's going to make it very light. So we're going to shift left. So that's going to increase our dinitrogen tetroxide and decrease our nitrogen dioxide. We have then made our reactants bigger and our products smaller. So that means our equilibrium constant is going to go down. That ratio is going to go smaller. Okay? Pressure. We're going to look at the number of moles on both sides. We have 1 mole of gas on our reactant side, and we have 2 moles of gas on our product side. So if I am increasing that pressure, I'm smooshing things together. I want to go to as small as possible. So 1 is smaller than 2, so I'm going to shift left. So if I shift left, that means my nitrogen dioxide is going to go down, my dinitrogen tetroxide is going to go up, but I have not changed the temperature. So that's not going to. Now, and if I decrease the pressure, that means I have room to expand. I'm going to decrease that pressure. I have lots of room. So I'm going to go to what makes more gas. So I'm going to shift right. I haven't changed the temperature. If I shift right, that means my nitrogen dioxide is going to go up and my dinitrogen tetroxide is going to go down. How do you guys do on that one? Okay, let's do another practice. Now this one's a little bit trickier because guess what? We've got some solids here. And solids do not become part of the equation. Remember, in equilibrium, we can only have aqueous or gases. Okay, so the only 2 things that we're going to really think of are the heat and this gas. So our equilibrium constant is really just carbon dioxide. That's it. Maybe we can think of our heat as well to just kind of give you that ratio. Okay, so here we go. The stress. Okay, note, this is what I was talking about. Adding solids or liquids and removing solids or liquids does not change the equilibrium. We only do gases and aqueous. This is because you cannot change the concentration of a pure liquid or a pure solid. They are 100% pure. It's only a concentration change that will change the number of collisions and therefore the equilibrium. Okay? So, stress. We add calcium carbonate. Calcium carbonate is a solid. So remember, it does not change. So none of this is going to change. No change. Calcium oxide is added. Once again, that is a solid. It doesn't shift the equilibrium. No change whatsoever. Carbon dioxide. This, on the other hand, is a gas. So if I add carbon dioxide, I'm making my product side heavy. So I need to make my reactant side heavier to match it. So I'm going to shift left. Okay? And since carbon dioxide is what we're talking about, I'm not going to do anything with that. And my equilibrium constant is not going to shift because I have not changed the temperature. Remember, temperature is the only thing that can change that equilibrium constant. Okay, temperature is decreased. So it is the same as taking this energy away. So it makes my reactant side really light. So I'm going to shift left to make more reactants. So that means my concentration of carbon dioxide is going to go down. And because my concentration of carbon dioxide is going to go down, that means my equilibrium constant is also going to go down because that is the products. The products go down, the equilibrium constant with temperature will go down. A catalyst is added. Remember, catalysts don't shift. There is no shift. It just gets us to equilibrium faster. Okay, carbon dioxide is decreased. So we're taking some of this carbon dioxide and we're taking it away. It's the same as making our product side light. So we're going to shift to our product side to make more products. So we're going to shift right. We have not changed the temperature. And we're talking about carbon dioxide, so whatever. It will increase eventually. Temperature's increased. So my temperature is increasing. That's the same as making my reactant side heavy. So I'm going to shift right to make that equilibrium. That's going to increase my carbon dioxide because my carbon dioxide is a product. And that, because it makes my product concentration more, and I've changed the temperature as well, it's going to increase my equilibrium constant. Carbon oxide or calcium oxide is removed. It's a solid. It's not going to change anything. So no change whatsoever. So solids and liquids don't change the equilibrium. All right, hopefully this practice made some sense. We'll talk to you later. Bye.